we need to reduce the step size. This is the function of the Euler methods in the book. The first input argument is the derivative term. The second is the independent variable vectors, including the initial and final value of independent. Y0 is the initial value, H is the step size. The last one is actually the internal variable. It can be used to detect how many input arguments you provide when you're calling this function. This is the command of the Euler methods. See here, yi plus 1 equal yi, and derivative term times step size. Let's discuss the stability of the Euler's method. When the step size is too large, we probably cannot get the converge. So how small we should take the step size? Look at this ODE equation. Minor a, the right hand side is the function is minor a times y. A here is the positive number. So the Euler method for this ODE equal here, right? We just plug the slope equal this, minor a yi, okay, times h, then equal this. If the absolute of this term is larger than 1, with iteration, we finally get the yi plus 1 higher and higher, and it will be infinite. So, to obtain the stability, we need to constrain this term less than 1. That is, h is less than 2 over a. So this is the condition to make the Euler methods stable. Here is the Hien methods, also called the improved Euler methods. For the ODE, standard form of ODE here, given the initial value, taking the step size first, then the iteration formula of a Hien methods is here two formula. The first formula is actually the Euler methods. We call the predictor. See here, right? The slope times h is the Euler methods. So use this estimate of y, and then we have the correctors. This formula we call the corrector. So yi plus 1 equal yi. So look at here, the slope. Actually, you see, this is actually the slope of the Euler methods here. And then using the estimate of the Euler method to calculate the slope, another slope. See here. And then taking the average of these two slopes. So the new slope. This is the new slope for the Hien methods, for the improved Euler methods. The local truncation error, LTE, is here. And then the global truncation error, square h, proportional to square h. That is the second order accuracy. Euler method is the first order, so this is improved, having second order accuracy. Here is the graphical description of the Heon methods. Look at this. The slope at Ti point is based on the Euler method. Using this slope, we can estimate one value of y at I plus 1. Here we estimate y I plus 1 at this. And then we also estimate that the slope, calculate the slope at this point using the first estimate here. Calculate the function. This is actually the slope at here. Then taking average of these two slopes, we get the new slope here. Average of two slopes. And then we have this correction. We get the yi plus 1. This is the solution of the Heon methods. So the key point is the average of the two slopes. One slope at the beginning of the interval and another slope at Ti plus 1 here. Here is the function of the Heon methods, the improved Euler methods. This function is similar to the function of Euler methods, except the iteration here. In the previous slide, we talked about the Euler methods and the Heon methods, the improved Euler method. Those two methods are actually two Longa-Coulomb methods. So here is the generalized form of the Longa-Coulomb methods. This is the general method, Longa-Coulomb methods. So see, this is the iteration, the general form. Yi plus 1 equal yi, right? This is the same. The difference is here. So this is the general slope of the Longa-Coulomb methods. Each step the same. Okay. So different numerical methods for solving the ODE-IVP are different in the slope. C1, C2, Cn are coefficients to be determined. K1, K2 lie here. See, K1 is actually the slope of the Euler method, right? And K2, this is general form. P1, Q11 are the other two coefficients. So standard, very complex. Again, Euler method is one of the Longa-Coulomb methods. So here is the format. We just rely the Euler method in the standard format of the Longa-Coulomb method, like this. Yi plus 1 equal yi h times k1. So k1 equal here, the slope. The Heon method is also one of the Longa-Coulomb methods. It's the second order. So we just rely the Heon methods in these formats, the format of the standard Longa-Coulomb method. Step side, right, times. You see, this is actually the average of K1 and K2. K1 is the slope of the Euler methods. And K2 is another slope. Okay. And taking averages.